This is the second in a series of videos about Gibbs Free Energy. In the last video, we derived an expression for Gibbs Free Energy, and we discovered that it involves the term delta S of the universe, which is our spontaneity indicator. And so now that we know what Gibbs Free Energy is, we're going to look at what the sign of the Gibbs Free Energy means about spontaneity. So we've made tables that look like this before in a couple of the previous videos about the thermochemistry chapter, where we look at the sign of the variables for energy going into the system and going out of the system. And this time we're just going to add one more column for no energy transfer to clarify what that looks like. So energy into the system means we're going to have positive variables. So if we have a positive value for enthalpy, we called this endothermic. If we have energy leaving the system, that's going to be negative. And if we have a negative value for enthalpy, we call that exothermic. We know this to be true. And if we have no energy transfer, delta H will equal 0. We'll just say that's no change. No heat was transferred. Okay, now let's add in entropy, which we've just started talking about in this chapter. So if the entropy is a positive number, this means you're going to have a disordered system, where the particles are moving freely, vibrating, translating, highest for the gas phase. And if we have a negative change in entropy, that means the system is going in a more ordered direction, like going from a gas to a liquid. If we have the change in entropy equal to 0, we'll just call this no change. No change in the order of the system. So now let's add our newest variable, Gibbs Free Energy. If our Gibbs Free Energy is a negative number, this is going to be non-spontaneous. Or we could say that the spontaneous reaction moves in the opposite direction of this reaction. If our Gibbs Free Energy is a negative number, the reaction is spontaneous. It naturally occurs that way. And if our delta G is equal to 0, the system is at equilibrium. And we'll talk about this more in the next chapter, but equilibrium means the system has reached its comfortable point and the energy is no longer going to be changing in one direction or the other. The energy will be constant. And so let's revisit which one of these situations is preferable, positive or negative, for each of our variables. So for enthalpy, we preferred this one. We preferred the exothermic reaction. Those were favored when the energy was leaving the system. For entropy, we preferred the positive number. The disordered orientation is favored because this is the most evenly distributed microstates. And for delta G, we prefer the negative number because that indicates a spontaneous reaction. So watch out for the signs of some of these variables. The negative delta H is favored and the negative delta G is favored, but it's the positive delta S that is favored. Okay, so now that we have our spontaneity indicator, our new favorite variable delta G, let's ask the question that we've really wanted to ask ever since the very first video of this chapter, which is my reaction spontaneous? And what we're really asking when we ask this question is delta G less than 0? Delta G is going to be the answer to the question we've wanted to know since the beginning of the chapter. Okay, So if we want to know if delta G is negative, we know it's going to depend on these other variables, on delta H and temperature and delta S. And we know already what the sign of the temperature is going to be. Temperature is listed in Kelvin. And there is no such thing as negative Kelvin, right? Absolute zero is 0 Kelvin. So this number is always going to be positive. So we don't really have questions about that, but we do have questions about the other terms. What is the sign going to be for delta H, and what is the sign going to be for delta S? And since we just talked about microstates for delta S, let's express this in terms of microstates, just for practice. So we have the number of states is the main number. So there's 2 possible states. Each variable can be plus or minus. And the exponent is going to be the number of particles or the number of variables. So the number of variables is 2. 2 variables, delta H and delta S. So 2 to the second power is 4 possible microstates. There's 2 possible situations for spontaneity. So let's make a table here right underneath the formula with 4 rows, 1 for each of those microstates. And let's try and figure out how changing the signs of these variables affects the spontaneity of the process. All right, so we'll make 1 column for each of the different variables. So we'll start with T, because we already said T is always going to be positive. Okay, so now what are our 4 situations? We can even draw a little histogram like before. We're going to have 1 situation where both variables are positive. We're going to have 1 situation where both variables are negative. And then we're going to have 2 situations where the states are evenly spread. 1 that's plus minus and 1 that's minus plus. Isn't that interesting how that all comes back to us? Okay, so let's choose the situation where delta G is definitely going to be spontaneous no matter what the numbers are. So what would that be? So we want delta G to be a negative number. So that means I want all of these terms to be negative. So I want this term to be negative. So delta H needs to be a negative number. And I want to subtract a positive term so that this one is also negative. And so that means I want delta S to be positive. So we have minus, minus, positive. And a negative number minus a positive number is always going to give a negative delta G. No matter what the numbers are, big or small, this situation is always going to be spontaneous. So naturally, that's going to be our favorite one. This is going to be favored exothermic, and it's going to be favored disorder. When both of the variables are favored, the reaction will definitely be spontaneous. So now let's look at the opposite situation. Let's look at definitely not spontaneous. So if it's not spontaneous, we want delta G to be a positive number, and we can do that by making delta H a positive number and by subtracting a negative number for delta S. So we'll have positive minus a negative number, and that will always, always, always give a positive number, because that's how math works. So this microstate is going to be always non-spontaneous. It'll be non-spontaneous when we have endothermic and we have an increase in order of the system. We can check off the microstates we already did here. So we did minus plus, and we did plus minus. So it looks like we've chosen the more evenly distributed ones in the middle. So now we need to look at both positive and both negative. So let's start with both negative. So if delta H is a negative number and delta S is a negative number, our qualitative math is going to look like negative number minus negative number. So this one's not as clear. We could have a positive or a negative delta G depending on how big these numbers are, right? If this number is bigger, then we're going to have a negative number. And if this number is bigger, we're going to have a positive number. So what we really want is we really want the reaction to be spontaneous. So what kind of conditions could we do? How can we change this variable and influence it towards that negative? Well, there's one variable left we can still change, and that's the temperature. So we can change how big the temperature is, and we can affect how large this term is to make the reaction go forward. This is something we do in the lab all the time. You change the temperature of the reaction to push it to happen in one direction or another. So what we really want is we really want to have a negative delta G. So we really want this negative term to be the biggest and this positive term to be small. So if we want to make this term with the T delta S small, then we want to make the temperature a low number. So this reaction can be spontaneous some of the time, and that some of the time is at low temperatures. Okay, I hope that makes sense. So if we want to make the negative number as large as possible and that positive number as small as possible by decreasing the temperature. That's our minus microstate. So now we just have positive left. So positive delta H, positive delta S. We are going to have positive number minus positive number, and it's going to depend. So how can we influence it? How can we influence it and push it towards a spontaneous reaction? We want delta G to be negative. So this is our negative term. So we want that to be as big as possible. And the first term is going to be a positive term. We want that to be as small as possible. And our adjuster knob is the temperature, and that's in the second term. So we want that term to be as big as possible. So we want to increase the temperature to make it spontaneous. So this microstate is going to be spontaneous at high temperatures. Okay, so even without any numbers, you can look at the sign of your delta H and the sign of your delta S, and you can automatically figure out whether a reaction is going to be spontaneous all of the time, some of the time, or none of the time. So now that we know about what the sign of delta G means and what the set of conditions are, in the final video, we will talk about how to do an example problem using this information, and we'll learn more about standard Gibbs free energy.